Let's start off on the right track with a simple statement. Fiat has won its spurs in the railroad sector because it is a big industrial complex whose members can share in a wealth of research. Fiat presents rolling stock and rail-based transportation systems. Fiat is a big industrial complex. Quite apart from automobiles, the name Fiat is linked to a wide range of sectors. Trains, as we have just seen, iron and steel, commercial and industrial vehicles, components, construction machinery, civil engineering and land use planning, energy, tourism and transportation, machine tools and production systems, and agricultural tractors. Most of these sectors have long formed part of the Fiat scene. Some indeed have been around almost as long as the automobile sector. The results achieved make it abundantly clear that production has been primarily directed towards one field rather than another, only in response to the country's political and economic needs. The same engineering and entrepreneurial skills, in fact, can be seen in every sector. Fiat's railway sector dates back to 1917, more than 60 years ago. It has been a pioneer in many countries and the source of many important innovations. Here, for example, is the world's first electric transmission locomotive. The date, 1924. 1931, in the period of the Great Depression, when the railroads were in serious trouble owing to the world crisis. Fiat's railroad sector introduced this light rail car. Within a few years, it could be seen in its thousands all over Europe. Another Fiat first worldwide, a gasoline-driven rail car. The photo was taken in Libya. These were the founders of a successful family whose descendants are still being built today. This long history of success is almost unique in the engineering world. It also offers a good illustration of the concrete advantages to be gained by a railroad manufacturer as partner in the many-sided Fiat complex. What, in fact, ensured that these rail cars would have such an extraordinary and long-lasting success right from the start? There's a very simple but surprising answer to this question. Their engines were not railroad engines. They were actually powerful truck engines built by Fiat's commercial vehicle sector and adapted for use on railroads. We have to remember that in the 15 or 20 years that elapse before it becomes out of date, any railroad motor with a good performance rating will be lucky if its sales amount to more than a few hundred units. Inevitably, it doesn't have much experimentation and work-up behind it, and the only way to offset this is for the manufacturer to provide efficient servicing all along the line, as it were. Now, if this were a Fiat railcar with a truck engine, such a melancholy scene would occur about once every 1.5 million kilometers. The regularity of a service is judged by how often the breakdown locomotive is called out, an unhappy event that happens 6 or 7 times less than with other forms of traction. The main reason for this is that truck engines are manufactured in as many as 70 to 80,000 units, not a mere 600 or 700. Since costs are spread over an output that is hundreds of times greater, much more time and attention can be given to perfecting an engine, instead of having to service it once it's on the job. Nowadays, truck engines are tried and tested for as long as 2 or 3 years. Quantity production is only started when there is a reasonable probability that they will need nothing more than routine maintenance during their working life. The Italian state railroads have realized that truck engine spares cost only 1/4 to 1/5 of their railroad-only equivalents. As a result, they have bought more than 600 units of Fiat's latest rail car, the ALN 668 alone, in a series of 13 orders stretching over a period of more than 20 years. A special point about the ALN 668 is that it is always equipped with the updated version of the most powerful truck engine on Fiat's current production list. It has also been the source of a dozen derivatives, suitably adapted for the needs of various foreign railroad systems. These have been supplied all over the world, from Venezuela, Mexico and Cuba to Turkey, Yugoslavia, Spain and Algeria. Here are 2 ALN 668 train sets undergoing trials in Sweden. What better proof could there be of the success of Fiat's formula than the supply of rolling stock to a country like Sweden, with its highly advanced industries and technologies, as well as a climate whose demands are very different from those of Italy. Added to this is the fact that 50 years spent in the development of railroad products within a firm such as Fiat have probably been much more thoroughly exploited and much more fruitful than in an ordinary factory concerned only with a single field. Fiat, in fact, has established a research system that acts as an ideal fulcrum for the whole group. This system operates through a research center, which is entrusted by Fiat's various sectors with the investigation of part of their medium and long-term innovation and manufacturing problems. These are solved by the center's experts with the aid of the latest and most up-to-date equipment and apparatus. The results obtained from the studies carried out to meet the needs of one sector are naturally available for use by other sectors. In this way, an extremely valuable common fund of knowledge and information is created. Lasers, for example, used in the experimentation of aircraft, can also be applied as an ordinary research tool in the railroad sector. This transmission part vibrated more than expected at certain frequencies during testing. The area concerned, the wall, is seen here painted white. Having applied a stressing device to the inner face, a holographic inspection is carried out. This technique provides a fascinating series of photos taken with a coherent laser light, from which the features of the vibration can be determined with the utmost accuracy. The holograms give us what amounts to a contour map of the micro vibrations that certain frequencies set up in the wall. This modern method undoubtedly enables one to track down the causes of the phenomenon with a degree of clarity that was not always possible with the lengthy and empirical methods of the past. The company's policy has been to keep the development of its several sectors abreast of each other, even at times when the economic future was not very promising, and to bring corporate research activities within a common system. The reason behind this clear-cut policy is very simple. Science and engineering in general never move forward in isolation. Each sector must benefit from the discoveries made by the others. In the end, every sector will necessarily be the same in terms of quality, reliability and costs, whether it makes automobiles, aircraft jet engines or trains. And so it is that the railroad sector has an enviable position within the vast Fiat complex, rather like that of a dwarf riding on a giant's shoulders. Small, yes, but able to take in distant horizons from his lofty perch. There is no time to examine all these horizons in a documentary, so we must take a few of the many subjects and discuss them thoroughly. This will give an idea of the style and the precision of our products. To begin with a very interesting example, there is the bogie assembly with which Fiat won the Eurofima competition. Thousands of Fiat bogies have since been manufactured in a few years for international and long-distance trains in Italy, France, Belgium, Holland, Germany, Switzerland and Austria. To understand the reason for this success, we must turn back the clock. What are the basic features of a passenger coach? As its name suggests, like the automobile, it is derived from the old-fashioned coach. Initially, it exactly copied the shape of a mail coach. Then, of course, the railroad went its own way, and there was a striving for more speed, more safety, more comfort for the passengers. All this, however, led to more and more parts and an increasingly complicated structure. It's obvious that one can't go on like this forever. You can pour a spoonful of sand on the balance pan of a water clock and it won't miss a beat. While a single grain of sand is enough to stop a more complicated mechanism. So if we've achieved a good standard of comfort and at the same time come to the end of the line in piling one structure on top of another, how can technological development be taken further without incurring the mythical curse of the Tower of Babel? Not by going back to simple things, because it is usually impossible to throw progress aside, but by bringing several discoveries together and reducing them to their essentials, as is done in all the more sophisticated technologies. A watch full of wheels becomes a quartz crystal watch. Yet how many years of research were needed to make such progress? The position is the same in the railroad world. Even today, most passenger coach suspension systems consist of a very complicated mechanical assembly. The desire to achieve optimum flexibility, of course, means that all these bits and pieces influence each other. The frictional forces, however, differ according to the stresses to which each part is subjected, and thus give rise to imbalances and wear. The excess play and rattling cannot always be kept under control after a certain number of kilometers. No what you'd call perfect shock absorption. Indeed, this is a common sight when one of these bogies with conventional suspensions comes in for overhaul after 300,000 to 400,000 kilometers. The bolts are so clogged up with rust that it's more convenient to cut them away with a blow lamp. That's not so bad, of course, and even fits in with the picture. What is worse is that the swing beam, which links the carriage and bogie, and should therefore rock freely between them for the suspension to work properly, is so solidly stuck in place that only this delicate and patient preliminary cleaning process can work it free. Nor should we really expect to find that a leaf spring has been able to keep its suppleness when its paint has formed a solid mass or earth has become packed in between its leaves. Here, in fact, is the traditional, though perfectly adequate method used to get the dirt off old-fashioned bogies and suspensions. Caustic soda. The passenger coach bogies now built by Fiat have done away with such complicated contrivances. A trim arrangement that has given excellent results, consisting of coil springs that act as the suspension and at the same time join the coach body to the bogie. Friction and wear are negligible compared with the conventional system. Seizing up is impossible, and thorough checking during the design stage has shown that constant performance can be expected. These enormous springs, the largest ever made for railroad use, are mounted on the motor bogie of the Pendolino tilting train, the world's first variable electric train set. Of the same design as those we saw before, they have shown that they can fully cope with the turning movement the bogie makes with respect to the coach body when the train takes curves 30% faster than ordinary trains. These springs, of course, are required to perform in a very unusual manner and must carry out a complicated series of functions. It goes without saying that their behavior must be checked down to the last detail beforehand. The characteristics of every single spring, therefore, are analyzed before it goes into service, during a thorough trial designed to ensure that its potential can be exploited to the full. It is well known, in fact, that any spring, however perfect, will tend to sag to one side or the other and bend along a preferred axis when compressed. Fiat therefore mounts its springs so that their compression characteristic work in opposite directions. This gives an even steadier ride. But it is one thing to examine a spring when it is firmly anchored to two perfectly parallel ends. Finding out how it will behave when under service conditions, when it has to carry a free-floating coach body, is quite another story. A second compression test is therefore conducted on correctly balanced suspensions mounted on locomotive bogies. Service conditions are simulated by a cushion of air that presses the suspension down with a force of almost 18 metric tons. This means that a film of air separates the suspensions from the compressor. They can thus move freely, vibrate and settle down on the bogie just as they would when supporting their full load at high speed. It's worth adding that in the case of locomotives, the payoffs offered by helical springs don't stop at more efficient suspension. Take the E633, for example. This is a 4,500 kilowatt electric locomotive designed to pull long, heavy trains even over tracks with tight curves. The Italian state railways laid down that the maximum two-axle bogie load should not be more than 40 metric tons to prevent heavy wear on the rails. The E633 therefore needs 3 bogies, and if traditional suspensions had been used, it would have had to be articulated, with all the mechanical complications this would entail owing to its size. Helical springs, on the other hand, permit a good 143 millimeter sideways shift of the bogie under the locomotive. The E633, in spite of its rigid frame, can tackle curves with a radius of only 90 meters. As you might expect, it's not such easy going for its stablemates of the same size. The modern E656, for example, is articulated, which, by the way, makes it heavier, 120 metric tons, as opposed to the 105 metric tons for the rigid body locomotive. Yet it has to give up much earlier. Curves of 140 meters radius are all it can manage. And that's not the end of the matter. Look how this E633 bogie behaves on a very uneven stretch of experimental track. The perfect grip on the rails cuts down sliding even under the most arduous conditions. Extensive tests on instrumented axles have shown that these wheels subject the rails to evenly distributed and extremely light pressure even on curves. The performance of this innovative system has proved so satisfactory that preliminary experiments are now being carried out on a ballasted mock-up of a single underframe with 4 two-axle bogies. This will be used on a locomotive with an output of nearly 7,000 kilowatts. During track trials, the 4 motors on the mock-up are driven by the coupled locomotive. As we said earlier, a few points are worth going into in detail. We've done the bogie. Now it's time to move up from the springs to the underframes. Here we see them being constructed by high-precision machinery that is far removed from the run-of-the-mill production equipment. This boring machine works on the diagonals joining the 4 axle box bearings with a precision measured in tenths of a millimeter. Hunting is cut down to a minimum. To make sure that the drawing specifications are maintained to the letter, this electronic feeler is used to check the workpiece whenever necessary, or any other part made in our workshops for that matter. Once again, however, the way in which things are moving today can best be understood by comparison with the technology of yesteryear. 40 years ago, this bogie frame was hailed as a pace setter. 63 parts held by a gaggle of 504 pins and bolts. Not that it was difficult to put together, since its parts were all arranged in rigid elementary geometrical shapes, squares, triangles, and rectangles. The stresses, however, had no chance of being evenly distributed. In spite of its rugged construction, therefore, this underframe was inevitably plagued by fatigue cracks at certain critical points. Now let's step aside for a moment and give nature a chance to show that those of her creatures to whom movement matters have no time for sharp-edged geometries. Over millions of years, her path of evolution has led to harmonic curves. These are stronger and more functional, though they exact their price in the form of more complicated engineering. Getting back to Fiat's bogie frame, we find that it only weighs half as much as the old-fashioned type, 1,400 kilos in fact. It's made in one piece, and its planned service life is longer than any other assembly, which means that it will never be the cause of trouble. Its profile is very reminiscent of that of a seagull. This accidental blending in with shapes already fashioned by nature is something that occurs with increasing frequency in the world of high technology. In this way, we discover that the apparently abstract concept referred to as aesthetic taste is really derived from the tendency to regard as beautiful that which is harmonious, and as harmonious that which is functional. High-level engineering and art indeed go hand in hand. Nature's harmonious shapes are the outcome of millions of years of evolution and selection. High-level studies, experiments, and tests must obviously precede their imitation in the form of mechanical equivalents. Structural analysis is employed at all stages in the building of rolling stock to investigate its mechanical, acoustic and thermal characteristics. It can be applied by Fiat sectors all over Italy, since they are directly linked to the facilities offered by the computer at None near Turin. This extraordinary system enables one not only to study a structure before it is built, that is to say in the design stage, but also to see how it will perform and make the necessary adjustments. Millions of calculations are required in the course of precise mathematical checks. These can be done in a few days instead of the months it used to take. They also do away with the sometimes nerve-wracking uncertainty that was associated with the first track trials. The company's experimental service, however, has the important task of seeing and eventually guaranteeing that the innovations proposed by the research center live up to their theoretical projections in practice. This is of fundamental importance from the safety angle. This red framework, for example, encompasses and tightens around a carriage for a compression test. The coach is first weighted with cast iron bars to simulate an all-up load. Highly sensitive strain gauges are applied at critical points to detect even micrometric deformation of the sheet metal under stress. A hydraulic jack then repeatedly subjects the coach body to longitudinal crushing stress of up to 200 metric tons. Here we see the underframe of the Fiat bogie chosen for Eurofema's prestigious European coach. These pictures were taken when it was being mounted on a fatigue test bench, where it was subjected to millions and millions of bending stress cycles lasting 3 months, equivalent to 50 years of service under the most trying track conditions. For the bogie as a whole, however, the fatigue bench is not enough. Vibrations generated by an ordinary hammer beating on the wheel rim are recorded by instruments to provide an array of data on the characteristics of the axle tree and how it will behave on the rails. A thorough checkup, in other words. In the next set of experiments, the axle, complete with its disc brakes, is placed in this sort of steel bunker for centrifuge testing at stresses 4 or 5 times greater than those likely to be encountered in service. Now it is time for a look round the workshop during an ordinary manufacturing day. This numerical control machine is programmed by a punched tape. Once the workpiece is mounted on the bench, it is machined on all sides without interruption. This rotating head can be automatically fitted with up to 36 different tools. It turns around the workpiece. In addition, the workpiece on its mobile platform can turn around the head. The combination of these movements reaches such a peak of virtuosity that this numerical control machine can work on a complicated rear axle casing without human intervention. Here is an even larger machine capable of handling a locomotive reduction unit casing in a single cycle. While one workpiece is being machined, the next one is placed on the other bench. This absence of downtime means that the time required with conventional machines is reduced from 5 to 8 times. Here, the finishing touches are being made to an electrical system of the E633, the locomotive whose bogies we saw in action earlier on. For nearly a century, the voltage fed to the DC engines was regulated in a very wasteful manner via a rheostat. This has now been replaced by the revolutionary chopper system seen here in red. The rheostat has disappeared, and voltage is regulated with no loss of power. Power electronics has made tremendous strides in recent years and is expected to become of increasing importance in the future development of traction systems. The Fiat Ferroviaria company has therefore taken a majority stake in a joint venture with AEG Telefunken, an international leader in this particular field. This step will serve to strengthen Fiat's standing as a designer and manufacturer of electric traction equipment. This body is being carried from one assembly line to the next on an air cushion just like a hovercraft. It is due to be flattened. What this means is that buckling inevitably takes place when the side panels are welded to the carriage framework. This must be straightened out by means of a thick plate that is vacuum attached to the outside of the metal sheet. The next step is the creation of shrinkage hotspots known as kiss mounts by heating and so expanding the inside of the sheet in many places. Since it cannot blister because of the plate clinging to it on the outside, each spot pushes into the sheet around it and forms a thick ring. When it cools down, it automatically shrinks and draws the thick ring with it, with the result that the sheet is flattened. But perhaps you're thinking, all that trouble to get a perfectly flat sheet, plus the removal of any remaining unevenness with special abrasive brushes, doesn't it add up to taking things a bit too far for a mere question of shape? A touch of filler would be enough to straighten things out. Yet the truth is that flattening and rubbing down are geared to painting problems. Sound paintwork, in fact, is as important to the life of a coach as the skin to the life of a human body. If the filler is laid on too thick, for example, the paint won't hold. Added to this, painting is no easy job. Up to a few years ago, of the 7,000 hours required to build a railroad coach, 700 to 800 were spent on painting alone. To make the wall perfectly even, 14 or 15 different passes were needed, what with fillers, rubbing down, anti-rust coating, transparent coating, brush lacquers, enamels and the rest. Even so, the warranties given in those days would not have satisfied the specifications now laid down for such coaches by the Swedish railways. Filler thicknesses, measured with a sclerometer, must not be greater than those on automobiles. As for the paint itself, it must be strong enough to withstand abrasion, in other words, highly resistant. This test was rather theatrical perhaps, but the message is clear enough. A dent, but no abrasion. The paintwork must almost shine like enamel. This is a sign of quality as well as being attractive. Yet even enamel hardness is not quite all that's needed. A bold jest indeed, but it shows that paint must also be elastic to stand up to extreme changes in temperature. This curl is a sure sign of elasticity. Hard paint would have simply flaked off. Yet elastic, unfortunately, means porous as well. And this paint is also expected to be fully waterproof, once again like human skin. No, better, because that twinge of rheumatism means that a little water has found its way through after all. In spite of severe specifications like those laid down by the Swedish railways, the time spent on painting coaches and mechanical assemblies at Fiat Ferroviaria in recent years has been greatly reduced. Modern sanding plants give an impeccable finish in next to no time. Here is a rust-covered underframe that has been subjected to subcritical annealing to release the strains built up during machining. After careful sanding, the essential prelude to sound paint adhesion, the part moves into a fully automatic circuit. Human intervention is only required when a different workpiece is brought into the circuit for the first time. The operator works the arm of the robot, which then remembers all the movements required for the actual painting process. Paint powders stick to the wall electrostatically. There is no waste inside and no pollution outside, since the color that does not stick drops down and is all recovered. The powdered workpiece then moves automatically into the next bays, where ovens melt the paint and bond it to the surface. Fiat's rolling stock and rail-based transportation systems sector is the largest enterprise of its kind in Italy. It has built 450 metro cars and trams, 700 locomotives, 7,000 coaches, 15,000 freight wagons, and 2,000 rail cars. What can one do with such a powerful setup? Practically anything, or at any rate, everything leading to progress in the railroad sector. With volume productions like these, The contribution of 20 or so original or innovative products is a very large percentage of the whole, and one that's hard to better. Fiat's Savigliano works with its 1,350 employees, Matera with 650, Reggio Calabria with 700, and the Cordova factory in Argentina with 1,200 employees have, we feel by their gradual expansion, borne witness to the fact that experimentation and research are always a fruitful investment.